without further ado, Phil on building RAG from scratch.
Thank you, Olga. Yeah, it's an absolute pleasure to be back at Programmable again and to see all of you. My name's Nash. I am a developer relations engineer at a company called DataStax. DataStax is sort of building a platform for building generative AI applications. So we have kind of two components for that. One is Langflow, which is a visual builder for generative AI apps. And that's a lot of fun to play with and experiment with as you're trying to kind of get to grips with all the various bits of the pipeline that you need for generative AI. And the other side is AstraDB, which is a vector database. It's also a sort of NoSQL document store. And we'll see a bit of that later. If you want to find me, I am all over the internet as Phil Nash, Blue Sky, Twitter, LinkedIn, wherever. Come find me. So today we're going to build RAG from scratch. And we're going to kind of approach what we need to do in order to make generative AI work a bit better for us in applications and in business. And to do that, we sort of have to deal with the problem with large language models. And by this problem, I do not mean the ethical problems that Chris was talking about earlier, I'm afraid. I am more talking about the idea of hallucinations, in which it's very happy to make things up confidently. And I love its confidence, but sometimes confidently wrong. Not only hallucinations, but also the fact that large language models have that sort of cutoff time for the knowledge that they kind of capture. It's sort of difficult to talk about, I guess, knowledge in terms of large language models, but the sort of relationships and the meaning that they capture gets a cutoff time. I think most of the OpenAI GPT models cut off in like October 2023. Google's Gemini ones are currently talking about stuff up till like September 2024, but like they still can't know anything beyond that. Like OpenAI ChatGPT does not know, as a basic model, does not know that Taylor Swift has released another album in 2024, and it's sad for ChatGPT, but worse for the rest of us. And then thirdly, like, there's data it can't possibly have captured because that's our data that's private, that's held internally to our businesses, to ourselves. Think about any kind of that internal business data that's private and not available to scrape off of the internet or wherever they've got all their data from. They can't have known that either. And if we want to build something with a large language model, if we want to use the power of generative AI to generate kind of human-sounding text, which is seemingly knowledgeable about something, we need to get that data to the model. And so the way we, I have a demo because we are demoing in this thing. And so I built a chatbot here. This is based on Gemini 1.5 Flash. So this is Google behind this. And I've told it to be an assistant that will tell us things about the Programmable conference. That's cool. All right, how can I help you? And I can ask, like, what am I talking about? And it simply doesn't know. I don't know who Phil Nash is. Never ask one of these models if they know who you are. It's always very disappointing. It's okay if they say, I don't know who they are. It's worse when they tell you about somebody else. Always does that to me. Anyway, so basically, this is a very basic chat bot that, where'd my code go? There it is. That is effectively just, let's find it. We've got a little prompt, which is trying to get like similar talks and stuff about the event, but this find similar talk function currently returns an empty array, so it's not very helpful. And so given that, we have a prompt that says, try to answer the following question. If you can't answer it from your conversational knowledge, you have to say so. And then we get the question, and then we talk to a bot, send a message stream, and get it back. And that's it. Like, that bot is just straight off to Gemini, no other help. We want to fix that over the course of this talk. And we're going to fix it using RAG, Retrieval Augmented Generation. This is a way to pass data, pass context to a large language model in order that it can answer questions based on that context. The idea is simply that we store that private data that we have somehow. A user makes a query to our application. We go and retrieve relevant data about that query. We provide that data as context to the model just inside the prompt, almost as simple as that. Alongside with that original query, the model generates a response. That's what they do. Something else, I guess, and then profit. We finally a use for generative AI. But the real problem here actually is that much of this is relatively straightforward now. Now those models have been built and there are APIs for them. Making a model generate text for us is actually really simple. And the tough part ends up coming into the retrieving relevant data part of the thing. Because when you are talking or chatting in sort of natural language to a bot like that, using that natural language to augment prompt is the challenge. And so this gets broken down, I guess, into like retrieval is basically search. It's a search problem. Augmentation is just the prompt, and generation is letting it go to the model. And so search becomes difficult. And thankfully, search is something that we have like dealt with over a long period of time. You know, the biggest companies on the internet are the ones that index the thing and search it. But we need to be able to do that using both natural language and on our data. And so this is not keyword search. That's where the natural language thing comes in. We're not talking to a bot in the same way that we would use an input in a search engine. So we're not searching by keyword. We're searching by similarity. We're looking for a way to search for content that can return things that we were talking about. Similarity search. And so that begs the question, how do we capture meaning for a piece of content in such a way that we can search for similar meaning and use that in our augmentation? And the answer to that currently is using vector embeddings. Vector embeddings is it's a list of numbers that represents the meaning of a body of text. That's my simple explanation. It's a little more complicated than that. So vector embedding really is, of course, a direction and a magnitude and a multi-dimensional space that represents the meaning of a body of text. And we'll see how that works as we go through this by creating our own simple vector embedding. This is where we're going from scratch. So there's a hypothesis I have for this one, that if we want to create a bot that is going to be useful to talk to you about this conference, say, the titles and descriptions of the talk kind of contain the meaning of those talks. That seems reasonable. They're made up of words. Also reasonable, I think. And so titles and descriptions that share words are probably similar. The talks about artificial intelligence and about large language models and generative AI will mostly say that in their talks, titles and descriptions. Although I did manage to check mine earlier and realize I never mentioned AI at all in my talk description, but it's not helpful for this hypothesis. But if we then collect all of those words and represent each talk as kind of a count of each of the words that they have in them, then we can do the same thing to a query, to an incoming kind of natural language query, count up the words that we've already seen in that, and compare that to all the existing talks and their counts of words. And that is likely to get us a similarity. And so let's try and do that. I'm going to go to the code, wherever it's gone to. There we go. And over here is my kind of implementation, or the start of the implementation for this. I have some data. In fact, so I grabbed all the talk titles and descriptions, and they're just here in a JSON array. And so right at the top there is Chris's talk from this morning. Mine's down there on level 6, kind of cool. And then the other AI talk that you're missing right now is Rob in the other room about AI-driven data security. At least he's talking about risks. And so I've grabbed all of that stuff, and I do have a little bit of code here already, which mostly is a case of just simplifying down all those words into lowercase without punctuation, without a bunch of common words. Because like if we share common words like me and myself and ours and all that kind of stuff, we're not really learning much about the actual contents of the talk. We need the non-common ones to really get the difference. And so most of that stuff, just takes text to words, just takes a set of text and turns it into lowercase without punctuation and all that kind of stuff. And so we've done that, and I've got all the talks from the JSON, so we need to go get all the words to start with. I like that, it's a good start. We'll take the talks and just flat map over them, because we want all the words from all the talks. And, oh, brilliant, Copilot is going to help me out. It's going to help me out incorrectly, because this is just an array. It's not an array of objects. So if we do that, we get all the talks, and so we can just check that to make sure that console.log all the words. And yeah, we've got loads of them. Loads of words. In fact, no, what I didn't do was make a unique array. So we'll just new set of, do a set of those, and we'll do an array of that set. JavaScript really should have just a unique function, but that's more like it. I was expecting 1,418 words. So you can see in this array of words, we've got the start of Chris's title, AI, hype, fuel, dumpster, fire, burn, planet, etc. And yeah, so 1,418 total words. So this is the size of our vector. This is the thing we're going to use to compare. So let's get rid of that. And we need to now take a talk or a set of text, which could be their incoming user query as well, and turn that into a vector of word counts. And so what we'll do is just create ourselves a word map, a little object there that's going to gather stuff, and yeah, we'll have the text to words of those words, and for those words, for each of them, Copilot and VS Code both working against me at this point, we'll actually do, yeah, that works. So for each word in our talk or user query, we're going to make an object which counts up the number of words that are in there. So that is, we'll set the key to word, and if it's either 0 or the existing number and +1. And that's great. But then that's just given us a word map. So actually what we want to do is that, thank you Copilot, which returns a map over the all words array, but now with the counts for all the words in their places. And so if we actually look at what happens there, we'll do text to vector for the first talk, cool. And we'll see that the first talk fills up the first 100 or so items of this array already, which is great. And the first, and if you can see it right down the bottom, like that first number there is 8. That means that Chris used AI 8 times in his talk, and hype twice. He actually didn't get back to dumpster or fire after the title either, which is nice to know. But then if we look at my talk is number 4, so it's mostly zeros here. Like it's not sharing many of the words with that first talk. We can see a couple of ones there. I'm not quite sure what they refer to, but that's good. If we actually look at 5, I think that's, yeah, Rob's talk. He's talking about AI. So he's talking about AI security risks, so he's got 3 uses of the word AI. So we now have this vector which is counting those words, and we can almost start to see bits of similarity pop up between them. Between Chris's and Rob's talk, like they're going to be more similar than mine and Chris's, because I didn't say AI. Really should have done, I guess. Cool. And so what we need to do in order to perform a search against all of our existing talks using our incoming user query is to create vectors for all of those talks. So that's nice and easy. We'll just map over the talks and return, in this case, an array which has the talk, the full text, and then its vector. And so if we then look at just logging that, just to make sure, I like to make sure these things have all worked as we go along the way. We get the vector, but we also have the text. There we go. AI is a hype-fueled, exactly. Cool. So that is it. We've created ourselves a vector. Now in this case, it's a sparse vector, which is mostly filled, for all the vectors are mostly filled with zeros. But that just means the numbers that are not 0 really count more, and that helps us here. But we don't know about comparing them yet. Comparing vectors then becomes our next challenge. We have these list of numbers, and computers, great with lists of numbers. They love them. But we need to be able to compare them somehow. And this is going to be great, because we get into vector search. And so I said earlier, these vectors are points in a multi-dimensional space. But imagining multi-dimensional spaces is really hard. I struggle beyond 3. And in slides, I only actually get 2 of them. So I've flattened this down just for an example. We've got a 2-dimensional vector space here with 3 vectors in it. And the question is, like, which vectors are more similar to each other? You might initially think it's the ones that are sort of physically closest to each other. And that can sort of work, but that's not ideal in this case. Because actually, sorry, I just called these points in space, but I said earlier they're actually, they are magnitude and direction. And so they actually, these 2 are not the most similar. It's actually the bottom 2, because the vectors are, magnitude and direction. And the direction is kind of their meaning, and the magnitude is how strongly they mean it. And so in this case, the 2 vectors in the circle there now are the most similar, because they're both pointing in the same direction. It's just that the one that's further out from the origin, further out from 0, 0 at the bottom left, just has been more forceful about it. And if you can think about that in terms of Chris's talk description and Rob's talk description, Chris has 8 times has used the word AI 8 times compared to Rob's 3. And so they're both about AI. It's just that Chris was like really about AI. And in this simple idea, at least anyway. And Rob's is slightly less about AI, just because it said it less. But they're both in the same direction. They're both leaning in the same direction. And so we can apply this in 2 dimensions. We can apply it to our 1418 dimensions that we just created with our word vectors. And then we can compare that using trigonometry. I was so confident when I left school, university, that I'd never have to see trigonometry again. But yet, here it is. Which means I get to impact the rest of you with mathematical things on a slide now. Sorry you have to see this. This is cosine similarity. It's how similar the 2 angles of a vector are. And it's actually, thankfully, one of the more relatively straightforward ones to answer, to explain here. We have 2 vectors, A and B, in this. And we're taking the dot product of A and B, so that's the dot product there at the top, or this thing here, which says for each vector in A, for each item in vector A and vector B, we're going to multiply them together, and then we'll add the whole lot up. So we're adding the first 2 of the second 2 and the third 2, and then we're just adding the sums up. That's fairly straightforward. That's nice. And then the bottom bits with the double bars there, that's magnitude. And so that's where we square each item in the vector, and then we add up all those squares, and then we take the square root of the lot. And so our cosine similarity is just the dot product, so the vectors multiplied by each other divided by the magnitudes multiplied by each other. And I get to show this ridiculous bit of maths, because let's go and see it in code, and we'll see it's far easier in code. Honestly, mathematicians should really consider JavaScript. We will see why that's not true in a minute. So the dot product, we take 2 vectors. We're going to take 2 vectors, and we're going to create a sum. And I'm just going to do it the simplest possible way. We'll just go for I is 0 to I is less than vec_a.length. See, what you'll see is my internet's gone off because Copilot has shut up, and I need the internet later. So I might have to, not in order to get Copilot to help me, but in order to ensure that the demo works at the end of the day, I need to just refresh this internet, I think. Stop it. Let's take me back on, and hopefully that gives me a login thing. Anyway, there we go. I knew it'd do that. I do agree to the terms and conditions. I won't have emails about it. Cool. So anyway, for each of the things there, we're gonna add to the sum. The sum becomes, vec a I times vec b. I see Copilot so much easier when it shows up. Plus equals. Thank you. And we'll return the sum. So so this is the dot product. We're just gonna loop over the first vector, and for each item in the vector, we multiply it by its equivalent one in the second vector, and we get the sum out. The magnitude then only takes 1 vector. And, look at it being fancy. I actually don't like that. I'm going to do the same thing. Let's sum, that's better. So we're doing the same thing. We're taking a sum for each item in the vector. We'll just square it, and at the end we return the square root. And that's it. That's all of, well, sorry, that's not exactly it. Then the whole full cosine similarity is just return the dot product of vector A and vector B divided by the magnitude of vector A times the magnitude of vector B. Much easier than mathematical notation, slightly more words, but we get there. And so what this means is we can now look at the cosine similarity of some of our talks just to check them out. Let's do it between, oh, that's the wrong way around, sorry, 5. We're comparing Chris's talk description to Rob's talk description. I'm still console logging something somewhere. There we go. Let's get rid of that. What we get is the answer 0.18162. This is going to be out of 1, so cosine similarity is between 1 and minus 1. 0 is kind of orthogonal, has nothing to do with it. Minus 1 is the opposite. We're not going to get any minuses because of the way we've constructed our vector. But in this case, Chris's talk description and Rob's talk description is 0.18 similar. But if I change that to mine, which was number 4, it's 0.019 because I didn't say AI enough times. But this is fairly reasonable. I did not say AI, and Rob has said AI 3 times, and thus those talks are more similar. And we can actually see this. Well, now we just need to return. We need to be able to do that query now. Do we need to do that? Yeah, let's go back to the slides. So that was okay. Oh no, we do need to do the query now, yes. I knew it. Right, so we get a user query come in and we want to find a similar talk based on that query. So we need to, first up, get the query vector. Which is text vector of query. We then need to, oh yeah, that'll sort of do it, won't it? Except for one thing. I do want to return the similarity as well. Oh, sorry, I need to return the vector as well. So if we do that, now I'm going to get, I've got console.log, find similarity, find similar talk of, not programming, let's not say programming, let's say AI. And we get 0 because I'm still returning an empty array. Cool. And now we get a few talks. There we go. So AI first software delivery. That makes sense. Legacy be gone. Could be something about AI. I'm expecting Chris's to be first though. And at the top there, how many are returning here? Shouldn't I be returning? Oh, I didn't limit this. That'll be why. So we're just going to slice 0 to limit rather than have all the talks. I forget to do one thing. Oh yeah, we actually need to sort it. That's correct. Because a vector search is actually really a vector sort. We're just sorting by the greatest similarity. And that is going to give us the answer. So if I now go back to the bottom, see which ones we provided. If I said AI, then we should get 5 talks here, and the first one is not Chris's one, didn't say AI enough times. It's actually pip install AI security, dependencies you can't ignore, which also should be interesting. And then Chris's, see, they used AI 11 times, the most AI talk. So that's good. But we can actually see this in a nicer way now because looking at my terminal is not the most ideal way of looking at this. I did build a search version of this as well. So if I say it again, if I say AI, we get that pip install AI security. Similarity is 0.6. It's actually pretty similar. That's the biggest, highest similarity I've ever seen when doing this insufficient kind of vector implementation. Then we get Chris's 0.5. We've got Jay's I need a husband AI beauty standards, which should be really good. But if we ask for retrieval, augmented generation, then it's my talk, hooray. And then, funnily enough, so this one probably has something about retrieval, a very less similar one. And then we get 0. We get 0 similarity because we've run out of words that we share, which is fine. Because if we actually take this to our chatbot and start saying things like who is speaking about AI, punctuation matters, then we have, that's the pip installs AI security with Chris, Jay, and we get this now decent answer. Now we're only returning 5 results and there are more than 5 talks in the thing, but I can also say like what is Phil Nash speaking about, and now it knows me, I promise. Speaking about building a retrieval augmented generation system, hooray! And what's interesting there, of course, is that I've still given it 5 results, and 4 of them are nothing to do with what I'm talking about, but this is where the generation side of things means that it's happy to only generate the bit that is pertinent to the query. And so yes, that worked, which kind of blew me away the first time, because that is a terrible vector implementation. We don't want to do that. It's still basically keyword search because we're matching against words, really. But we've done it with maths now instead of by looking at it. And there's other problems with it too, right? We needed to know all the data up front. We needed to know that in order to know that our vector was going to be 1418 dimensions, because that was the number of words we had. And then the query is, of course, sensitive to that vocabulary. Like if I go and ask a query that shares none of the words with those 1418 words that we captured, we'll get useless results. If we added another talk that had more words, we'd have to extend that vocabulary. We'd have to extend our vector of 1418 dimensions to use those more words, and then we'd have to do, then our dot product becomes harder because we have a longer vector to loop through on every occasion. And the same word can mean different things. I can't think of any other thing that hype fuel dumpster fire could mean, but it could mean different things. What I wanted to show, actually, I missed one little bit, which was being able to compare the same talk to each other, which actually I think is interesting. If we look at comparison of, the same talk with itself. This is what I meant by JavaScript and maths don't agree. That's just floating points. It's fine. So if you add the same words, sometimes it's 0.999 like that. Sometimes it comes out as 1.0003, which is also fun, because it's now more similar to itself than it ever could be. So we have this problem with this vector implementation. And so a better way around this is to use an embedding model. Embedding models are machine learning models that have been trained to place similar concepts and similar ideas in the same point in their multidimensional space. And they are much more complicated than my simple words match kind of idea. They have been trained with an awful lot of data in order to kind of get this meaning. It's very similar in the way to a large language model works in a way, but the result of calling an embedding model is that you get a vector back. And so there are many of these available. You can run them yourself. You can run them using libraries like transformers, which work in both Python or JavaScript. Of course, there are API versions available, and this is the sort of OpenAI version of that. They have 3 text embedding models at the moment. They have their older one, text embedding Ada 02, and the newer ones are text embedding 3 small and 3 large. This is just how you'd create a vector embedding with text embedding 3 small, which gives you 1536 dimensions. Text embedding 3 large gives you 3072 dimensions. Now I have in my head the number of dimensions that many embedding models take up, and that's just taking up space that could be used for other stuff. But it's nice to know at times. 1536 is what you get out of this. And then the other side of things is that we're only dealing with, I don't know, how big is my JSON file there? We've only got 30 odd talks in there. And so if I had 30,000, then doing that vector calculation, doing that dot product and that magnitude for each and every single talk in the data in my data set, that would blow up my machine eventually, because JavaScript's not built for doing that kind of thing. But even if you were to do so using like a Python and PyTorch or something that's highly optimized for doing vector calculations, eventually you still don't want to do it against everything all over the place. And so a better result for that is to use a vector database to store this. Vector databases store things which mean, 1, you don't have to keep them in memory, but 2, they implement indexes so that your vector search can be achieved much quicker than quite literally comparing vectors against every single other vector, which would be too much work. Vector indexes, I think, are really interesting. I don't quite have time to go into them right now, but because they're indexes, there is some sort of approximation. And so what we actually built in code with our made-up vector was a proper like k-nearest neighbors search. But a vector database and a vector index is actually an approximate nearest neighbor search. That they're mostly good at getting the closest ones, but it is an approximation just due to the optimizations done to make sure it works quickly. And so AstraDB is DataStax, our database, and has a vector index for it. And I do really like it for two reasons. One, it does make things very quick. The vector index that we use is it's called JVector, and it's based on a Microsoft paper called DiskANN, which means that not only as a vector index is it very accurate, but it actually, based on that research from Microsoft, is able to be a vector that is bigger. The index can be bigger than memory. It doesn't have to be entirely held in memory. Which, if you have millions and millions of vectors, does eventually become important to you. So this is using it. It's a straightforward API. This is the JavaScript version, and if you have a vector, you pass it in as $vector, and that's nice and easy. But if you don't already have a vector, it can create vectors for you as well. It's one of the niceties about a database being built kind of, or improved in this world of generative AI, is that we can actually just vectorize content as it goes in. And you just set your collection up with a model that it's going to use, and it will handle that for you, and I really like that. And then on the other side, like searching for things, like I said, it's sort of a vector sort. And in this case, again, if you've got your collection set up, you can just vectorize your query as it goes in. You don't have to worry about it. And you get your results back. And yeah, I have a pre-existing implementation of this. So everything that we wrote in this file, which is now getting to almost 200 lines, although a lot of those lines are those common words, everything that we wrote here has been replaced here with the database, and we just go to the collection and ask to vectorize it. So I already vectorized the talk data and put it in the database before the talk, but now if I do a sort and vectorizing it, I can do that, and if I go to my server, I can replace our bag implementation. It's kind of like a bag of words is the idea of that implementation. And we replace it with vector search. And I go back to my search, for example. If I now search for, I search for AI, what do I get? Yeah, height field densifier. So the most similar is now Chris's, not because he said AI that many times, but because it was merely about it. And then J's comes up as a 0.71, then the AI security one. And if I search for like AI and RAG, my one comes up. Yes, cool. Now I said RAG a bunch of times, but I never said AI in this talk, in this description. Yet it's still 0.75 similar, which is very cool. And that means we have much more useful similarity scores for these results now, because the vector that we're using is much more sensible. It's based on that embedding. I think it actually is text embedding 3 small is what I used for this. It's the OpenAI one. And it's also nice to point out that then, if I go back here, we're still going to get the same results here because our original vector search sort of worked, but now it works better. What is Nash speaking about? And it will tell me. Hooray, I will be live coding a thing. Yes. What's interesting, what's important to note there is that if the vector search is using OpenAI's embeddings and it's using Gemini to do the generation, the embeddings don't have to match the generation because in the middle of it, the actual augmentation is still just turning the whole thing to text and passing it over. You don't have to use any one particular embedding. And in fact, there are embedding models that will work better for you depending on how they've been trained. If you happen to have specifically, like the OpenAI ones that I've shown there are kind of general purpose ones, which work really well for just most talking about stuff. I think there are specifically trained embedding models out there for stuff like legal data and things like that, where the vocabulary can be quite different. And if that's outside of the embedding model's training, then it doesn't know how to make up a useful vector. And so if you do have specialist kind of data to look at, you may need to look into either an existing pre-trained vector embedding model that will have like a context about your environment, well, not environment, that's not the right word, a vector model that have context about the topic area that you're talking about, or if that doesn't exist, you may need to look into sort of fine-tuning an existing embedding model to use or to augment it with understanding of your context. So that's RAG. That's retrieval augmented generation. We built a terrible version from scratch, but then we replaced a couple of little bits of it. We replaced our vector embedding implementation, and we replaced the memory store with the vector store, and we got a good result. There is a lot more optimization that can be done to this kind of thing, from augmenting like your initial user query to kind of using a bigger search, getting more information. A bigger responsive documents, which you then do sort of a re-ranking on using a different model at the end of your process. But the very basics of RAG are right there in that we do a vector search, we vectorize our content, we store it, we search against it, and we put it back to our generating model to come up with the answer. I've got some more interesting kind of stuff which you might be interested in. The next slide has a QR code on which will have these links. But if you are interested in more of this kind of stuff, there are alternative ways to vectorize content, for example, such as there's a technique called Colbert, which doesn't vectorize a full passage of data. It vectorizes each word in a passage of data, and then you get a vector for every word, and then you compare that, which is mad, but it allows it to understand things that are outside of its training better, because it kind of uses a sliding window of context. It is crazy, but go have a look at that. Alternatives for other ways of dealing with it is the idea of graph implementation for this. If you break up your data, but then kind of link it to each other, using a graph to then spider through that, through those links, can allow you to bring back context that wouldn't have been found by the vector search, but is important for the generation side, or answering the thing. So check out that post on content-centric knowledge graphs. And then finally, like, vectors don't have to be used for generative AI. The first thing I did with AstroDB when I started at DataStax was to build a sort of just a feature for my own blog, which gives you the related posts at the end. Because if you vectorize a bunch of blog posts and then you look at one of them, you can see that a whole bunch, you can see what they are most similar to. And that seemed like a great idea to me, so that's there. Other than that, as I said, the slides are behind that QR code and a bunch of links on there, including other ones I do keep adding as well. Again, yeah, my name is Phil Nash. I'm a developer relations engineer at DataStax. I wish you all the best with any work you do with generative AI and not burning down the planet. Thank you very much.